So, welcome to today's lecture. If you recall, we had started looking at the notion of continuity for functions of a real variable and its applications in our subject. We looked at continuous functions and we were looking at what is called the intermediate value property for continuous functions, which stated as follows, that let f be a function defined on an interval a b to r which is continuous. So, the function is given to be continuous and alpha and beta are two real numbers which are in the range of the function. That means, that there are points x 1 and x 2 belonging to a b such that f of x 1 is equal to alpha and f of x 2 is equal to beta. So, the function takes the values alpha and beta at some points x 1 and x 2 in the domain. Then the claim is that for every real number r between alpha and beta, there exists a number c such that between x 1 and x 2 such that f of c is equal to r. That means, if two values alpha and beta are taken by a continuous function, then every other value in between alpha and beta should also be taken by the function at some point. So, this is the intermediate value, because it says that any value in between alpha and beta should be taken at least once by the function if alpha and beta are taken. So, this is a property of continuous functions, and we had seen in the previous lecture what geometrically it means. It means that there is no break in the graph of the function. Once you start plotting the graph of the function from the point a comma f of a to b comma f of b, once you start plotting drawing the graph, you should not lift your pen till you reach from the point A to the point B. So, that is, and mathematically this theorem means that the images of intervals are intervals. So, a very special case of this theorem would be when alpha is a number less than 0 and beta is something bigger than 0. So, the theorem as a corollary of this, if f is a continuous function, so that f at some point x 1 is bigger than 0 and f at x 2 is less than 0, then for some point in between x 1 and x 2, the function should take the value 0. That means, for a continuous function, if at some point the graph is above the x axis and the graph is at some other point the graph is below the x axis, and if the function is continuous, that at some point in between it must cross the x axis. So, there must be a point c where the value is equal to 0. So, this theorem has applications in lot of applications in mathematics, but let us see one application in our subject of So, let us take a demand and supply functions of a commodity are given as the following. So, the demand function, demand is a function of the price. So, demand is equal to 100 minus 2 p, and the supply is again a function of the price, and that is equal to 3 p. So, essentially this is a system of two linear equations in two variables, and one can find what is the price where demand will be equal to supply. So, that is what is called the equilibrium price. The price p 0 where demand equals the supply is called the equilibrium price, and that value is called P E of the commodity. If in this case, if you want to solve these equations, we can put the value of P from one equation to the other and solve. So, d P E is equal to S P E, demand is equal to supply, that is another way of doing it, and that will give you that this equation, demand is equal to 100 minus 2 P E is equal to 3 times P of E. So, that from here you get P of E equal to 20. So, when the price is equal to 20, demand will be equal to the supply and there will be equilibrium. And there is I want to illustrate this in another way as follows. So, let us so geometrically this system of two equations, when you solve, you get this price P E equal to 20. So, this red one is the demand curve, that is a linear curve 100 minus 2 P E, and the supply is equal to 3PE. So, that is a linear equation passing to the origin. So, these are the two graphs of these two equations DPE and DP and SP. So, wherever they cross, that is a point where that is a point P of E. So, that is a common point, that is a point of equilibrium when demand equal to the supply. So, that is P of E. So, that is okay. Solving it geometrically or solving it by system of linear equations. Let us look at another way of solving this, namely, let us look at those two equations, right, and at the price when P E is equal to 20. So, you get both to be equal to demand is equal to. So, that is finding at what when the price is what is a demand and what is a supply, both are equal to 60. Another way of solving this would be that let us consider the function f of p, define a new function which is demand minus the supply. So, demand is equal to 100 minus, so demand function, if you recall, was 100 minus 2p and supply was equal to 3p equal to 20. So, let us put those values in the two equations. So, let us find f p which is d p minus s p. So, simplify this 100 minus 5 p. So, for this function, if we want d p equal to s of p, that is same as saying that we should have a point where f of p is equal to 0. So, what we have to show is, and so this is equal f of p is equal to 0. Now, note that d of p is a linear function. So, that is a continuous function. S of p is a linear function, that is a continuous function, so, right. So, and we can observe that from here, if p is something say 100, then this value is negative, right. P is 100, then this value is negative. If p is equal to say 5, then this value is positive. So, there are points where the function takes positive values and there are points where the function takes the negative values, and it is a continuous function. So, by intermediate value property, there will be a point where we will have f p equal to 0. So, demand will be equal to supply. But in general, finding a point where this f of p is 0 for a continuous function, say intermediate value property just says that there is a point where the function will cross the x axis if it is positive at some point and negative at some point, but it does not tell you what is that point. So, this is purely an existence theorem which ensures the existence of a equilibrium. For example, it does not say what is the point of the equilibrium. So, that is one has to find some other ways of locating that point. In our case, it is not very difficult because the functions are simple. So, this will be so because at some point, so we can find out these points, right, because linear function. So, it is okay, f of p it's also is a linear function. So, you can find out that, but in general it may not be easy. So, but at least in many complicated problems where you want to show that there will be a point of equilibrium, this existence theorem is quite useful. So, intermediate value property of continuous functions comes handy when you want to show the existence of a point where the value is 0. So, there is we said that the property of intermediate value property says that the image of an interval is an interval under continuous functions. Here is a slight strengthening of that result. It says that if the domain is a closed bounded interval a b. So, note that here is a closed bounded interval. So, f is a continuous function on a closed bounded interval. Then there exist points, let us call 2 points called x min and x max belonging to the domain a b, such that f of x, the value at every point in between is bigger than f min and is less than or equal to the value f max. That means, this also indicates that for a continuous function there are bounds, that the range of the continuous function has to be bounded by the value f x min and f x max. That means, there are two values, you can call this as small m say and call this value as a capital M. So, let us just write this property. Let me draw a picture of this. So, let us say this is a function. So, this is the point A and this is the point B, and let us say the graph of the function is something like, it goes like this. So, this is the value and this is the value, this is the value. So, this is the point f of A and this is the value f of B. So, saying that this is a continuous function, so there is no break in the graph of the function, and what we are saying is there is a point where the function takes the minimum value. So, in this case, for example, at this point, if you call this as x min, so this is the value, let us call it as m, which is nothing but f of x1, and there is a point obviously in this case this is this point. So, this is also f of x max. So, this point is also equal to x max, right. So, it says that the graph of the function will lie between these two lines. So, that is what it says. So, if f is continuous function on a closed bounded interval a b to r, then it says that f of x for every value will be less than or equal to f of x max and will be bigger than or equal to f at x min. Means, so another also, this also says that the range of f is equal to, if I call this as small m, call this as capital M, so small m to capital M. So, this is the value small m and this is the value capital M. So, this theorem says that if f is a continuous function on a closed bounded interval, right, a b, then it is bounded. That means, there are two numbers small m and capital M. So, that the range of f is equal to small m to capital M. That also means that the smallest value is attained at some point. So, there will be point x min which will be equal to m small m and x max which will be equal to. So, one way of just understanding this theorem is that for a continuous function on a closed bounded interval is bounded and attains its maximum and the minimum values. So, we will see applications of this theorem later on when we want to do optimization problems in economics, commerce and management problems. So, this is what is called the min-max property of continuous functions, right. So, next we look at a concept in our subject, what is called the marginal of a function. So, what is marginal of a function? This concept of marginal of a function is an important concept, and it is applicable, is useful in analyzing decision making problems for a short run when it is possible to change an input. The input can be changed for a short run. So, we will try to make it precise mathematically what it means. So, what we are saying is, in every business model, one wants to ensure that the benefits of certain activities outweigh the cost in order to be profitable, right. So, that is what the any business is about. So, one tool for weighing this relationship is called marginal analysis. So, how is it this, what is this analysis? So, let us look at that. The cost and the benefits of a small change. So, marginal word in English means small, which can be very marginal is something which can be neglected in English, but we are saying that the cost and the benefits of a marginal change in the production of good or an additional unit of input for a good. So, what is the relationship of this vis-a-vis cost and the benefits? So, let us for example, let us like a toy making firm might be using how they can use marginal analysis to determine the potential benefits of increase in the production. Some firm is making toys and they want to know how this tool, what we are saying, can be used in analyzing increase in production. So, let us say These are applications of this decision making, namely that we can allocate our resources in a better way. So, this is all why this tool is useful, marginal analysis. So, let us see what this marginal analysis is. Let us look at a company which is producing 50 smartphones in a day. So, the company is producing smartphones, and they are their capacity at present they are able to produce 54 smartphones in a day. They the cost of producing 50 phones is rupees 25,000, right. So, that is the cost of producing this. So, selling price of each smartphone is rupees 800. So, and there are 50 smartphones. So, that gives them a revenue of 40,000 rupees by selling those 50 phones, right. So, now the company, if the company produces 51 smartphones, if they increase their production by one smartphone, the total revenue would be, one more phone is sold, earlier it was 40,000, one more phone sold means 800 rupees. So, the revenue will be 48,800 rupees. And what will be the cost? The cost of producing the total cost will be 25,850, right, because 50 phones. Okay. So, when we divide by that cost of producing each, so total cost will be 25,000. There will be one additional cost. So, should the company be producing one more smartphone or not? So, this is the cost of producing 51 phones. This is the revenue they get. So, what we get is the marginal benefit. That so, marginal means one more phone is produced, the 51st phone is produced. So, 40,800, that is what they are getting, and minus 40,000. So, total will be 800. So, that is a marginal benefit they are getting. And what is the marginal cost? Cost is 25,800 minus 25,000, right. So, the cost is marginal cost is 850. So, that clearly indicates that they will be at a loss of rupees 50 if they produce one more phone. So, just by analyzing the production of one more, keeping the price, selling price same, leads them to decide that they should not be producing more phones. So, the net benefits fall by 50 rupees. So, they should not be producing more phones. So, this is how marginal analysis is used in deciding whether you should be increasing the production or not. So, let us formally define for a function y equal to f of x, its marginal at a point x 0, function has a domain, x belongs to some x. So, formally we are defining now what is called the marginal of a function is defined as the result of output, right. So, defined as the result on the output by a additional unit of input. That means, at the point x 0, if x 0 changes to x 0 plus 1, what is the change in y that comes, right. So, that is called the marginal of the function y. So, note that so what we are saying is increase in a unit input, right, output will change marginally. So, note that when x is changed to x plus 1, y will change to some value. So, the marginal is again a function of the variable. So, given a function, its marginal is again a function, right, a function of the same variable x. So, let us look at another example to illustrate this. Consider the input output model for a function given by y equal to 2 of x, where x is the labor employed. So, this is the input output model, input is the labor and y is the output for labor. So, it is a linear function y equal to 2 of x. So, it clearly indicates this is if you increase x, y is going to increase, because the slope for this linear function is positive. So, it is going to increase. So, increase in output, anyway from this formula it is clear that if we increase the input x by 1, then output is doubled, it is 2, right. If if x goes to x plus 1, right, then this will go 2x plus 2. So, y will increase by 2 units. So, doubled in the sense that if y was something, so increase in 1 gives a 2 times increase in y. So, right. So, the marginal of this is equal to 2 for every x, right. So, marginal is equal to 2 for every x. So, it is quite clear, right. So, when x goes to x plus 1, the difference, right, y will change by 2. So, m p of x is equal to 2. So, m p indicates this is the marginal of p. Okay. This is what is called marginal of the production, right, output or the production for every x increase. So, that is 2. So, there is a constant, marginal is a constant function. However, notice that more output is generated even when the large inputs of labor are there, even if other are fixed. So, in this model, if x keeps on increasing, the y keeps on increasing, right. So, because the marginal is positive and that is 2. That does not seem to be a very good scenario, but because normally increase in the labor and keeping everything else constant does not increase the production. This seems a contradictory to the business model. So, what is to be done? So, in fact, one would expect that the larger inputs of labor, other factors remaining fixed, should reduce the output and it may become 0, output may become 0. Right. So, let us look at some illustration. So, marginal should not, the idea is that marginal should not be modeled as a continuous function. To give a illustration of this, let us look at a particular example. See, the example is that of a thermal power station, which has a capacity of 1500 megawatts per hour as and the input is coal. So, it is a thermal power station. So, input is coal, coal is put in to generate heat and then steam and then gives the electricity, run the turbines. So, electricity produced is produced and the capacity of that thermal power plant, the maximum it can produce is 1500 megawatts per hour, right. So, in a day, so let us calculate how much the power station can produce in a day. The maximum it can produce in a day is 1500 per hour. So, 24 hours. So, that gives 36,000 megawatts of. So, this should be per day. It is not per hour. So, that should be per day, right. So, let us say that 250 kg of coal is required to generate 1 megawatt of power. So, this much of coal is required to generate 1 megawatt of power. So, that means the unit of quintal of coal increases in output will increase output by. So, if I put a unit, 1 unit of increase, that means 1 quintal of coal, if we increase, then the output will increase by 1000 divided by 250, that is 4 megawatts per hour, right. So, that is clear. So, keep in mind that 250 kg of coal is required to generate 1 megawatt of power, right. So, 1 quintal of coal, so we divide by that, so that is 4 megawatt is, so that is okay. So, if 1 unit increase will give me 4 megawatt per hour. So, what does that mean? That means that the marginal output per day for coal is 4 till the plant reaches its maximum output. So, this is a marginal, right. So, marginal for the thermal power plant, if we increase the input, that is a coal, by 1 unit, then it increases by 4, right. So, this is 4 megawatt per hour. So, that is till it reaches maximum. So, that, and when will it reach maximum? It will reach maximum for how many quintals are required to reach the maximum? Maximum capacity is 36,000. So, x into 4 is 36,000, that is 900 quintals. So, when x is 900 quintals, the plant would have reached its maximum capacity. That means what? That means after that, even if we bring in more coal, increase, then the capacity is not going to increase, the power is not going to increase, the production is not going to increase. So, that means what? The increase in labor, if you bring in more labor to bring in more coal, the increase in labor will increase utilization of more coal, and hence more production till the maximum is reached, right. And after this increase in production is reached, even if there is no even if there is an increase in labor, the output is not going to increase, because that is the maximum capacity of the plant. If I look at the y, the marginal product, so y x is the marginal. So, marginal remains 4. So, this is the marginal of the product. So, marginal remains 4 till it should be 9,000 here, till now 9,000 is reached, and then suddenly the marginal becomes 0. Even if you increase in x, there is not going to be any increase in the marginal, is not going to change, right. So, this is what the marginal curve looks like for this scenario. So, there is a discontinuity for this, right. So, there is a discontinuity at the point x. So, that is good enough. Okay. So, normally marginals will be discontinuous. So, in a model for economics, one tries to bring in models in economics, so that the marginals are not continuous functions. So, that is the conclusion of this analysis. So, we will continue with our what we have done till now is looked at the notion of limit, notion of continuity of functions, and we have looked at some properties of special properties of continuous functions. Namely, one was the intermediate value property and the other was the min max theorem, and both of them will be used later in our analysis. And we have tried to define what is called the marginal at present in a very informal way here. We will come to the marginal when we discuss the notion of derivative a bit later. At present, what we have looked at is marginals for mainly linear functions. They turn out to be constant functions, right. So, we will continue our study of functions and their properties in the next lecture. Thank you.